All right, hello and welcome to our Thursday edition of Chem 305. Last lecture of week 6 after we finish today, which it'll be a long one, right? We've got office hours. We will be officially 75% through our entire course, which is crazy. So after today, give yourself a 75% done high five. Go us. Excuse me, I don't have a ton or any really business items to discuss other than what was it? Chapter 9 practice homework will be posted soon, as well as an update, some information on exam 3 to guide your study this weekend, because exam 3 opens a week from tomorrow and closes a week from Sunday. So we're approaching that milestone. Mile marker. Oh, wait, hang on. There we go. Okay, so we closed lecture on Monday talking about oxidation states, learning how to assign oxidation states. And again, I want to kind of focus our attention. We're still talking redox reactions. Whoa. That's a very, very thin marker. So today we are continuing our conversation on redox reactions. Again, we haven't even actually gotten to actually unpacking, looking at redox reactions yet. We've just been focusing on assigning oxidation states. Sorry, Parthon, I just saw your comment. So I'm not ready yet to comment on the scope of the exam 2. All the pertinent information will be in the forthcoming post, which the reason why it hasn't been posted yet is I'm still kind of working out the details. At least chapters 7 and 8 will be on exam 3, possibly some of chapter 9, but I haven't exactly determined that yet. So keep your eyes peeled. All right, so today we're going to be diving into actual redox reactions, and we spent a lot of time yesterday learning how to determine the oxidation state of every element in a compound. And the important thing to remember about oxidation states, there's two things you want to keep in mind. First, the oxidation state reflects the amount of charge each element has in a compound. All right. They're not actual charges, but they reflect the amount of charge, the amount, whether they're electron rich or deficient, the amount of charge each element has in a compound. And then secondly, and this is the clutch concept, changes in oxidation state tell you if an element tell you if an element is gaining or losing electrons in a reaction. All right, and this is the part that we really want to zero in on, because we know losing electrons means that it is being oxidized, and gaining electrons means it is being reduced. As we learned yesterday, losing electrons is oxidation, gaining electrons is reduction. All right, now, with all of that in mind and that kind of refresher in place, let's use our knowledge of assigning oxidation states to analyze the problem, the chemical equation that I wrote up on the board yesterday. I wrote that the the combustion of hydrogen with oxygen to produce water. I told you this was a redox reaction, and yet we looked at it and we were like, well, but there's no electrons. Where are the electrons? And that's when we learned that it's our job to determine who's selling electrons, who's buying electrons. And we do that through assigning oxidation states. All right? So, first off, let's look at hydrogen. And you'll notice that hydrogen is, we can use our first rule, right, for assigning oxidation states. We know the oxidation state of every element present must add to the total charge on the molecule, on the species, and we have a charge of 0, which means that hydrogen's oxidation state here will be 0. Same story for O2, right? Oxygen has no charge, and so the oxidation state of each individual oxygen in the molecule of O2 must be 0. All right, now when we go to the product side and assign our oxidation states to H2O, all right, we have a hydrogen in this molecule, rule number 2. It's not the, it is present with another nonmetal, so it has a oxidation state of +1, all right? Now we can determine oxygen's oxidation state because we know 2 times the oxidation state of hydrogen plus the oxidation didn't mean for that to be green, plus the oxidation state of oxygen has to equal the total charge on the molecule, which is 0, right? So we have +2 plus the oxidation state of oxygen is equal to 0. And then we subtract 2 from both sides of this equation. So the oxidation state of oxygen in the molecule of water is a -2. All right, now, all right, now that we've assigned our oxidation states, we can determine which element is oxidized and which element is reduced. All right? So, what you want to do when you're trying to figure out who's being oxidized, who's being reduced, is look for changes in oxidation state. The first change I see is with hydrogen. It starts at 0 and ends at a +1. All right? So hydrogen started with 0, ended with a +1. That means that hydrogen has lost electrons in this process, right? It started at 0, then it got positive. That means it's lost negative charges. Kate, great question. You can. Kate was wondering if we can ignore the stoichiometric coefficients when determining our oxidation states And the answer is yes. You can always ignore your stoichiometric coefficients. All right. So so hydrogen here has lost electrons, and when we lose lose electrons, that means that hydrogen is oxidized. All right, hydrogen is oxidized. Let's look at the other change we see. We start with a 0. We end with a -2. So we see a change in oxygen's oxidation state, and we see that if you start at 0 and end negative, that means you gain electrons. All right, you gain electrons, which means that oxygen is reduced. All right, so hydrogen, the element, is oxidized in this process. Oxygen, the element, is reduced. All right, now here's a question that I have for you. Here's a question that I have for you. What causes hydrogen to lose electrons? All right, what causes hydrogen to lose electrons? What compound reacts with hydrogen, causing that loss of electrons? And the answer to that question is the molecule O2. O2 causes the oxidation. All right? And if we ask the same question about oxygen, what compound reacts, causing that oxygen to be reduced? The answer is H2. H2 causes the reduction. All right? And so because O2 is the molecule that causes the oxidation, we say that O2, oxygen, O2 is the oxidizing agent. Because it is the reagent, it is the molecule that causes hydrogen to lose electrons. In a similar fashion, because H2 is the compound that causes oxygen to gain electrons, we say that hydrogen gas, H2, is the reducing agent. Right here. Let me abbreviate to save some room. All right. O2 is the oxidizing agent, the compound that causes the oxidation in hydrogen. H2 is the reducing agent because it is the compound that causes the reduction in oxygen. All right. Now here is the key piece of kind of terminology that you need to keep in mind. In redox reactions, we say that individual elements are oxidized and or reduced all right, so that's the first thing. So we talk about oxygen, the element, or hydrogen, the element, being oxidized or reduced. And then when you talk about the reactants, however they appear, in the chemical equation, the reactants that cause the oxidation or reduction are the oxidizing or reducing agents. All right, so individual elements, when you talk about elements, you can talk about being oxidized or reduced. When you talk about agents, oxidizing and reducing agents, you're talking about reactants, however that species appears in the reaction. Susan, that is not a silly question at all. Oxidation is it's, to put it simply, oxidation is just losing electrons. Or you could think of it as having your electrons stolen. By another molecule. Oh, I wrote molecule. Oxidation is a general term. There are a lot of different processes that involve oxidation, but all it means is that electrons have been lost. If electrons have been lost, oxidation has occurred. All right. So let's do a few examples. Totally. Whoops. All right. So for each of the following reactions, let's determine the oxidizing agent and the reducing agent. For the following reactions. Let's see. So, simply put, when we talk about individual elements being oxidized, all right? So if you look at the previous example, we say that hydrogen lost electrons, so the element hydrogen is oxidized. Oxygen, the element, gained electrons, so oxygen, the element, is reduced. But the oxidizing agent is the compound that reacts with hydrogen to cause the oxidation. The reducing agent is the compound that reacts with oxygen, causing the reduction. So the agents are reactants, the elements individually get oxidized and reduced. And we'll see that fleshed out in the next few examples. So let's determine the oxidizing and reducing agents for each of the following reactions. Now the steps to completing this are as follows. First, when your delta problem like this, you've got to assign your oxidation states. All right, so step number one is going to be determining what the oxidation states are. For everything in the reaction. Step two, find the atoms that are oxidized and reduced. And then step three, is determine the reactants that caused the oxidation and reduction. All right, so that is your three-step process to doing a problem where they say determine the oxidizing agent and reducing agent. All right, so example number 1. Let's look at the reaction between calcium and chloride that produces calcium chloride. All right, step number 1, we need to assign all of our oxidation states, right? We need to determine which one is being oxidized and which one is being reduced. Now, on the reactant side, when we first look at calcium, calcium has no charge, so its oxidation state is 0. Cl2, likewise, no charge, so its oxidation state is 0 as well. All right. Now let's look at our product, calcium chloride. Rule number 1 can't help us yet. Rule number 2 can't help us. We don't have hydrogen, but rule number 3 does. Whenever you have a metal in the first 2 columns, its oxidation state will be equal to its normal ionic charge, and calcium's in the second column, so its regular ionic charge will be a +2. And once we know calcium, we can determine chlorines, because we know the oxidation state of calcium plus 2 times the oxidation state of chloride adds to our total charge, which is 0. Carolyn, that is not a dumb question. Great question. So the reason why they have no charge, my answer might sound dumb though. Okay. The reason why they have no charge is, okay, this is going to sound dumb. Just bear with me. The reason they have no charge is because they have no charge. You're like, what? And I say yes. So, for example, if I asked you what the charge of this is, you would tell me that the charge is +2 because it's written right there, correct? If I ask you what's the charge of this, the charge is still written right here. It just happens to be 0. There's no charge. All right, so if you have a compound where there's no, or compound, an element, whatever, where there's nothing written, superscripted to the right, that just means it has a charge of 0. Now, Brianna, often halogens are +1, but they're not always +1. All right, they can be. +1. Halogens. Well, I can actually think of an example where they would be. Halogens usually are -1, but when you look at Cl2, we've got no charge up here. Our charge is 0, so that means 2 times the oxidation state of chlorine has to equal our total charge, which is 0. And when you divide both sides by 2, we find that in the molecule Cl2, chlorine has an oxidation state of 0. Esther, are the charges for oxidation states determined based on the position of the element tooth and noble gas, like we learned in the previous chapters, but called something else. Okay. Esther, that's a great question, and the answer is sometimes. Okay. Okay, so here's the deal. The thing you got to remember about the rules for assigning oxidation states is you always take them in order. You always do rule number 1 first. Then, if rule number 1 can't help you, move to 2. If 2 doesn't help you, move to 3. If 3 doesn't help you, move to 4. They're ranked in terms of priority. So you don't ever jump to rule number 3. Rule number 3 says, oh, calcium's plus 2. If rule number 1 gives you the answer, as it does here for calcium, this thing has no charge on the species, because we know that the oxidation state of every atom in the species has to add to its total charge. Since our charge on calcium metal here on the reactant side is 0, its oxidation state must also be 0. We'll see that calcium has a plus 2 charge for the calcium chloride, the product, because it's in a compound, all right? But you have to apply rule number 1 first, then 2, then 3, then 4. If you don't, then you're going to get oxidation states that are out of whack. Basically, Karenza, the reason why it's 0 is right here. You've got 0 charge, so this is a rule number 1 scenario. Totally. Yes, you only move to the lower rules if the first one doesn't bail you out, or the earlier ones don't bail you out. Okay, so with that in mind, let's take a look. So that is why calcium and chlorine on the reactant side both have oxidation states of 0, because we know that the individual oxidation states of everyone present have to add to the total charge. And on the reactant side, calcium atoms have no charge, chlorine, a molecular chlorine, has no charge. Yep, Karenza, you got it. You got it. Okay, so and as you'll see, I'm about to play out that the calculation right here. So we know our charge of there we go. We know our charge on calcium right now is a positive 2. So we have plus 2 plus the oxidation states of 2 chlorides, equals 0. So now we subtract 2 from both sides of this equation, and we get 2 chlorides together have a charge of negative 2. Then we divide both sides by 2 to realize that chloride has an oxidation state of negative 1 on the product side of this equation. All right, so these are our oxidation states, which I will hurriedly read right here. 0, negative 1, 0, and a positive 2. The positive 2 came from rule number 3, which says whenever you have a metal from the first 2 columns on the periodic table, they'll take their normal ionic charge. Yeah, rule number 3 for the oxidation rules. All right, so we have assigned our oxidation states. Step number 1 is good. We're there. Oh, not right now. Not right now. No, babe, not right now, babe. Okay. All right. Collect my thoughts. Okay, let's see. Where are we? So we've assigned our oxidation states. That's why I miss a classroom. But c'est la vie in Rona season, right? Okay, let's go. Number 2, finding the atoms. So we've assigned our oxidation states. Now we need to find the atoms that are oxidized and reduced, right? We need to find the atoms in this reaction that are oxidized and reduced. And to do that, you need to identify which atoms are experiencing changes in their oxidation states. Calcium starts at 0, ends at positive 2, so that's a change. Chlorine starts at 0, ends at negative 1, so that is a change. All right? Once you've found the atoms that experience changing oxidation states, then we can determine who's oxidized and who is reduced. Esther, great question. Almost. So the sum of all the oxidation states always equals the total charge. Here, the charge on everything in this reaction every species in this reaction, every reactant product has a total charge of 0. So for this reaction, yes, there are other times where you won't have a total charge of 0, and so that's why I stated it that way. But here, because everything has no charge, because everything has no charge, the sum of all the oxidation states will add to 0. But you won't always have situations where there's total charges of 0. Okay, so we've identified where we are experiencing changes in oxidation states, and now we have to determine what is being oxidized and what is being reduced. All right, so first let's look at calcium. Calcium goes from 0 to positive 2, right? Its oxidation state is getting positive. That means it has lost electrons, right? Oops. We're talking about calcium loses electrons, which means that calcium is oxidized. All right, lose electrons, oxidation. Now, here's my question. Well, actually, I'm going to put that question on hold. Let's look at what happens with chlorine first. All right, chlorine also experiences a change in oxidation state, starts at 0, ends negative, right? Ends at negative 1. So that means chlorine gains electrons. All right? Chlorine, the element, gains electrons, so we say that chlorine is reduced. All right? Chlorine is reduced. Once you've determined the atoms that are oxidized and reduced, you're ready to move to the third and final step, which is determining the reactants that caused the oxidation and reduction. All right, so the question is, what reactant reacts with calcium to cause the loss of electrons? And the answer is Cl2. All right, Cl2 is the reactant that caused the loss of electrons in calcium. So Cl2 is the oxidizing agent. All right. Chlorine now gained electrons. When you ask yourself, what is the reactant that caused chlorine to gain electrons, the answer is calcium. All right? Calcium caused chlorine to gain electrons, so calcium is the reducing agent. All right? And this third step is what we're being asked to do in this problem. Are there any questions before we do another example? Because we're going to do another example involving redox. Okay. All right. Let's hit it then. Let's do another example. Consider the reaction. Again, this one's borrowing from a recent lab between magnesium metal, HCl, and hydrochloric acid to produce H2 and magnesium chloride. All right. So, step number one, we need to assign oxidation states for every species in this reaction. All right, so starting with magnesium. Magnesium has no charge, so in this species, magnesium metal, since it has no charge, it has an oxidation state of 0. All right. Now let's look at HCl. All right. HCl. We rule number 2 tells us that hydrogen will always be +1 unless it's the only nonmetal present. Chlorine is a nonmetal, so hydrogen is +1. If hydrogen's +1, that means chlorine has to be -1, right? Because we know that hydrogen plus chlorine have to add to our total charge, and HCl has a charge of 0. Moving to the product side of the equation, hydrogen has no charge. All right, hydrogen has no charge, and so hydrogen in H2 has an oxidation state of 0. Okay, and now finally we have magnesium chloride. This is going to take a little more heavy lifting. Magnesium is rule number 3. It's a metal in the second column of the periodic table. So it has an oxidation state of +2. And with that knowledge, we can use rule number 1 to figure out what the oxidation state of chlorine is, because the oxidation state of magnesium plus the oxidation state of both chlorides have to add to our total charge for this molecule, which is 0. All right. Now, subtract 2 to get chloride isolated on one side of the equation. 2 times the oxidation state of chloride equals -2. And then we divide both sides by 2. So chlorine has an oxidation state of -1 in this compound. All right, so we have assigned all of our oxidation states. Whoops. All of our oxidation states for all of our elements. Now we have to figure out so we've done step 1, assigned oxidation states. Next we have to find the atoms that are oxidized and reduced. To do that, you have to find which elements are experiencing changes in their oxidation states. And one change that I see is in magnesium. It goes from 0 to +2. The second change I see is in hydrogen. It goes from +1 to 0. All right. You'll notice that chloride, that chlorine, the element chlorine, on both the reactant and the product side of this reaction, has the same oxidation state. It's -1 on both sides, so it is not changing. It's neither being oxidized or reduced. Magnesium and hydrogen, however, are exchanging electrons. All right, chlorine is just a innocent bystander. So we've found the atoms that are oxidized and reduced. Right, magnesium is going from a 0 to a +2. So we say magnesium loses electrons. Which means that magnesium, let's see, lose electrons, oxidation, right? Leo. Magnesium, the element, is oxidized. When you look at the other element with changing oxidation states, it's hydrogen. Hydrogen goes from a +1 to a 0, so hydrogen gains electrons. Which means that hydrogen is reduced. No. It's well, we are in a microwave right now. That is Yep. That is exactly what's happening. That's running water. I'm streaming from our office, and the water pipes run like right around here, which probably means someone's taking a shower or a bath or something. My apologies again. Yeah, there's a lot of things that I like, or I appreciate about a classroom now that we don't have one. There are no kids interrupting the stream lectures, and there's also no random showers making you think you're in a vacuum or a microwave. Okay, so magnesium has lost electrons, so it's oxidized. Hydrogen has gained electrons, so it's reduced. Now, the question that we have to ask to do step 3 is, what reactant causes magnesium to lose electrons? And the answer is the reactant that causes magnesium to lose electrons is HCl, hydrochloric acid. So hydrochloric acid is the oxidizing agent. The second question we need to answer is, what reactant causes hydrogen to gain electrons? And that reactant is magnesium metal. So magnesium is the reducing agent. All right, and that is what we've been asked to find for this reaction. All right, so that is this problem. Let's see, let's do another one. let's take a look at, let's see how we're doing on time. We're doing okay. So let's determine the oxidizing agent and reducing agent for the reaction between NH3, ammonia, and oxygen gas. That's a 7. To produce... yes. Kate, great question. Oops. Oops. So, Kate, great question. What if there are more than 2 reactants? And the answer is the reactants with changing oxidation states will always be the oxidizing and reducing agents. There sometimes are reactants that don't have elements that are oxidized or reduced. They're part of the reaction, but they're not part of the electron exchange. And those you just ignore. So the compounds, the reactants that have the elements with changing oxidation states in them will always be your oxidizing and reducing agents. So let's look at this reaction between ammonia and oxygen gas to produce nitrogen dioxide and water. All right, so step number 1, we need to assign our oxidation states. Now, with our first reactant, rule number 2 tells us that hydrogen will be +1 because it's always +1 when it's with other nonmetals. And so if hydrogen is +1, oh, sorry, that is, wait, hang on. There we go. That's a stoichiometric coefficient of 7. All right, 702. All right, now we have to figure out our oxidation state of nitrogen. Since hydrogen is +1, the oxidation state of nitrogen plus our 3 H's has to add to 0. So nitrogen plus 3 equals 0, which means nitrogen must have an oxidation state of -3 here. In our molecule of O2, oops. There we go. In our that looks a little bit like an H, that +1. I just want to clarify it. +1. In our molecule of O2, we have a charge of 0, so oxygen bears a charge of 0, or an oxidation state of 0. Now for NO2, We don't have any hydrogens. We don't have any metals in in the first two columns. So NO2, we have to resort to the fourth rule, right? Which is the more electronegative element takes its normal ionic charge. And so oxygen, being more electronegative than nitrogen, will have an oxidation state of -2. Now we have to find, the oxidation state for nitrogen, because we know the oxidation state for nitrogen plus 2 times the oxidation state of oxygen equals our total charge, which is 0. So nitrogen plus 2 times -2 is 0. So nitrogen minus 4 is equal to 0, and when we add 4 to both sides, we get that the oxidation state for nitrogen in NO2 is a +4. Alright, +4. Last but not least, we have H2O. Hydrogen is a +1, and oxygen, we've got 2 times H plus oxygen is 0. So that means 2 times +1 plus O is 0. And if we have a +2 plus our oxygen, plus our oxygen being equal to 0, then subtract 2 from both sides, and we get an oxidation state of oxygen is -2. Alright, so we have all of our oxidation states for every element in this reaction. Alright, now, so that's step 1, longest step 1 ever, right? Now that we know our oxidation states, we have to find the atoms that are oxidized and reduced, and to do that, you need to identify who's undergoing changes. Now you'll notice that hydrogen is 1 on both sides, no change. Oxygen is 2 on both sides, no change. Where we see a change is with nitrogen, starts at -3, ends at +4, and we see a change with oxygen, starts at 0, ends at -2. So these are going to be the elements that are oxidized and reduced. Taking a look at nitrogen first, we see that nitrogen starts at a negative, ends at a positive. It's lost electrons. So nitrogen loses electrons. You know, sometimes that is all you can do to survive. Sometimes it's all you can do is to survive, to just take notes and keep rolling, and then when you come back to it, you work some problems, start unpacking it, it'll click. It'll click. Because you can see, you start at -3, end at +4, you've lost negative charges, right? You've lost electrons in this process. And if you've lost electrons, that is the definition of oxidation. So we say that nitrogen is oxidized. All right? when you look at how oxygen has changed, oxygen starts at 0, ends at -2. So oxygen, if you go from 0 to -2, you've gained electrons. Oxygen gains electrons in this process. And gaining electrons is the definition of reduction. So we say that oxygen is reduced. All right? Now let me ask you a question. So oxygen gains electrons. Kate, great question. All right, so oxygen gains electrons. What causes oxygen to gain electrons? What reacts with it that causes that gain in electrons? And the answer is NH3. NH3 reacts with oxygen, causing the electron gain to happen. So we say that NH3 is the reducing agent. All right, we could ask the same question. Nitrogen loses electrons. What reacts with nitrogen to cause that loss of electrons? What reactant is involved? And the answer is O2. O2 is the oxidizing agent because it causes that loss of electrons in nitrogen. And this, again, is what we were asked to do in this problem. All right? Okay. Let's see. You know, I was kind of planning on getting to collision theory today, but I don't think it's going to happen. We have about 10 minutes left. Let's do this. Because I could work another example, but I feel like what needs to happen at this point is for all of you to take this knowledge, kind of apply it on your own. So let's here. I'm gonna grab an example I'm going off script. Grabbing an example from my notes. Or not in my notes. Yes, I'm working on, Esther, to answer your question. I am working on, and I almost have it done, the practice homework for chapter 9 will be getting uploaded soon, and that has tons of examples. Okay. I'm going to leave you with this example. Again, it's determining the oxidation state. Determining the oxidizing agent and reducing agent for this chemical reaction. But I'm not going to do it. I'm going to leave it with you and allow you to take a crack at it, and then we can maybe try it in office hours if you want to, or you could ask me about it later. And the reason why I'm assigning another one of these is the nice thing about these problems is you have to, because a lot of people are asking for examples for just problems where you're assigning oxidation states, but you do have to assign oxidation states in these problems actually to everything in the chemical equation, so they tend to be pretty comprehensive. I need to move this down just a little bit. All right, so zinc sulfide reacting with oxygen gas to produce zinc oxide and sulfur dioxide gas. All right, so give this a try. Take a crack at this problem. Again, I'm almost done with the homework that should be going up in between now and office hours. But really, to let this sink in, to kind of let it solidify in your mind, you just have to do just a lot of examples. Put in a lot of practice, and it'll make sense. Alrighty? So let's go ahead and we'll put a pin in lecture here, and we'll be back. I will be back at 3, and hopefully you'll all join me. Thank you so much, and I'll see you in a few.